Hello and welcome to the 19th Caithness International Science Festival. We're delighted to welcome you tonight to this, the second of three events from Caithness Astronomy Group, who have been great stalwarts of our festival. They're helping us to get to know our celestial neighbour, the moon, a little better. I'm Ian Bakey, Chairman of Science 03. Here with me tonight is Nicola MacLeod, the festival coordinator. Joining us from the Caithness Astronomy Group are Gordon Mackie, who will deliver the featured presentation, Neil McLean, Kristen Willem, who, weather permitting, will deliver the carrying out live observations, John Hilton and Ian Darby, who will be moderating and assisting with the Q&A. Also joining us tonight is Professor Keith Nicholson. Before we begin, I wanted to just plug our activity book. Nicola and the Science Festival Committee have put together an activity book with lots of puzzles and competitions, and it's available in Tesco and Lidl in Wick and Thurso, unless it's gone. But if they're there, you should be able to get it if you look around. And if you can't find it in Tesco and Thurso and you want it, Tesco and Wick and Thurso or Lidl and Wick and Thurso, then please go online onto our website and it's downloadable too. Before we begin, a little bit of housekeeping. The event is being recorded, but your screens are not. This has been a popular event, so please direct all your questions through the Q&A and Caithness Astronomy Group will handle them, and they'll try to answer as many as they can. As an audience, you have the opportunity to upvote questions. That means that if you give it a thumbs up, it goes higher up in the list and therefore it gets answered quickly. I'm now going to hand over to Gordon Mackie for tonight's presentation, part 2, the moon in motion. Over to you, Gordon.
Thanks very much, Ian. I'll just share my screen and we'll get started with the presentation. So if we can just get a quick thumbs up from folk. Are you seeing the first slide in the presentation? Excellent. Okay, we're good to go. So as Ian has said, this is part 2 of our guided tour of the moon. So the main topic tonight is looking at the moon in motion. So we'll be quickly looking at how the moon formed, what causes the phases of the moon and what causes eclipses. And then the plan was to do some live streaming, and that's where the rest of the team were going to be helping. So in the bottom right, you can see Neil McLean and Christian Wilhelm. They were going to be doing live observing through a telescope and streaming the views as part of the presentation. Unfortunately, it's not going to be possible tonight because of the cloud. The moon is well hidden at the moment from the parts in the county we have telescopes set up. But what that does mean is, while we're going through the Q&A, there is a panel of folk here, and I will probably do the same as I did last night and call upon my expert colleagues to pitch in if there's any questions that I'm not in a position to answer. But they will be monitoring the questions as we go along. So feel free to post your questions between now and the end of the session. Okay, so first of all, how did the moon form? Well, the moon didn't form at the same time as the Earth. The main theory that's accepted these days is that it was the young Earth, which was only a few million years old, was impacted by a protoplanet roughly the size that Mars is. And what happened next I'm going to explain in the next couple of slides. But the main reason that this impact theory is considered to be the the most obvious one to have happened is because there's lots of evidence supporting that, in the form of the chemistry of the Earth and the Moon, the orbit that they're currently in, and the speed of the orbit of the Moon round about the Earth. So there's lots of supporting evidence that we can see nowadays that suggests that that was the origin of the Earth-Moon system. There are other theories. I'm not going to go into them in detail. I'm just going to briefly cover in this short talk the theory that's most accepted. So, as I pointed out, the theory is based on there being a giant impact when the Earth was fairly young, and what that did is it greatly damaged the Earth and threw lots of material from the impacting body and from the impact site of the Earth into space, and that then formed a disk around the Earth. So what you ended up with was a lot of debris floating in a disk around the Earth shortly after this major impact happening. And then over time, possibly as little as a few hundred years, the material started to accrete. So basically what that means is it started to amass together. So as the bigger lumps were orbiting round about the Earth, they swept up the smaller parts, and eventually what we ended up with was the Earth, the larger body in the centre, and the Moon orbiting around it, and all of the smaller stuff was either collected by the Moon as it orbited, or the gravity of the Earth caused it to be pulled in onto the Earth's surface. So that's essentially what happened, or what we believe happened. Obviously, there was nobody about 4.5 billion years ago to witness the event, and I suspect if they were on the Earth at the time, they wouldn't be about to tell the tale afterwards anyway. But we have some evidence that supports that theory, and there's been lots of computer simulations have been carried out that also show that that sort of thing would happen from the initiating event. So we ended up with the Earth and the Moon orbiting around it, and initially the Moon was much closer than it is today. Today it's, as you can see on the screen here, just shy of 400,000 kilometres. So that's, for people my age, that's 250,000 miles distance between the Earth and the Moon. So quite a distance, but in astronomical scales, that's pretty close. It's certainly your next door neighbour when it comes to things in space. And just to give you an idea of what the scale is then, in relation to the size of the Earth, the size of the Moon, and the distance in between, if you imagine that the Earth was the size of a football, then the Moon would be roughly quarter the diameter of a football, which is about the size of a tennis ball. And the distance between them, as they orbit nowadays, would be roughly 23.5 feet. So you might think that means there's a lot of space in between, and you'd be right. In current spaceships, you're talking a good couple of days traveling to get from the Earth to the Moon. But like I said, that really is very close when it comes to the other distances relating to other objects in space. Now, if you don't like working in kilometres or miles, somebody has worked out that that's the equivalent of 29.5 billion hula hoops between the Earth and the Moon. I'm not sure who first thought of using that as a unit of measure, but there you go. There's an interesting fact that's unlikely to turn up in a pub quiz. So the Earth and Moon as we've already mentioned, are there with the Earth at the centre, the more massive body, and the smaller moon orbiting around it. So if you look at the animation in the bottom right, you'll see the Earth rotating, the moon orbiting around the Earth, and obviously the Earth and moon system orbits around the sun, which is at the centre of our solar system. So that's the sort of overview arrangement. And because of the motion of the Earth and moon around the sun and the moon around the Earth, there are a couple of things that are a consequence of that. And I'm going to talk about them now. That's the phases of the moon and eclipses. The one thing to point out at this stage is that the moon does not emit any light. All it does is it reflects light. And as a result, there is one half of the moon is lit by sunlight and the other half in darkness the whole time. And as it orbits around the Earth, in the night sky, it appears to change shape. It appears to change appearance. And that's referred to as the phases of the moon. So you can see in the top left, we've got a crescent shape. And then you get slightly thicker crescent. You've got the half of the disk illuminated here. And it eventually gets a larger and larger proportion of the disk illuminated until you can get to full moon. I don't have a full moon here, but let's talk about how these phases are generated. And it's really all down to the motion of the moon around about the Earth, which takes about a month to occur, in the region of 4 weeks for the moon to travel around the Earth. And as it does so, depending on the position of the moon, so we've got the Earth in the centre, we've got the moon orbiting around the Earth, and the sun is off the screen away to the away beyond the top right hand corner. And what you see is, as the moon orbits or circles around the Earth, the lit side of the moon will become more or less visible from observers on the surface of the Earth. And as a result, the moon will change phase. So let me just quickly move on to a simulation here that you can look at on a website online. So you'll notice the web link at the bottom. And this is a great simulator for you to fully understand what happens motion-wise of the moon around the Earth that then causes the phases of the moon. So I'm about to play the video that will show the moon go from new moon, which will be when it's round here, all the way around via the various phases to full moon, which is here, and then back again to new moon. So the equivalent of roughly a month's worth in Earth days. But before we do that, I'll just point out we have the Earth in the centre here. In this case, the sun is way off the screen to the left-hand side, shining light in this direction as shown by the arrows. So the side of the Earth facing the sun is obviously the daytime Earth, and the opposite side is nighttime. And as the moon goes round, the sunlit side will be the direction pointing towards the sun. You'll not be surprised to hear that. And in here, this illustrates what the lunar phase looks like during the moon's journey in its orbit around the Earth. The bottom right-hand one, I wouldn't worry too much about it at the moment, but just so you know, if you're going to play with this simulator at home later, it kind of shows where the moon and the sun would be in relation to an observer, in this case, on the Earth. So don't worry too much about that just now. Just concentrate on this, the position of the moon as it circles the Earth and what the phase of the moon looks like. So let me just play the video. So we're currently at new moon, which is when the moon's on the sun side, moves round until you get half of the moon illuminated, and then when the moon is directly opposite the sun in the sky from Earth, you have the full moon, and it continues round, and you see the phase change again, you get crescent, and it will finish again as a new moon 4 weeks after the time when it was passed there. So that's how the phases work. Hopefully that made sense, but as I said, that simulator is available online, and you can go on and you can play that simulation at your own speed and make sense of all the information that's available there so that you better understand how the phases happen. Now, as a consequence of the moon orbiting the sun, there are other things that can happen. One of the most spectacular is that we can have eclipses. And an eclipse is when a celestial body or part of a celestial body goes into the shadow cast by another celestial body. So for us observers on Earth, what we are going to talk about here is when we have a solar eclipse and a lunar eclipse. So a solar eclipse happens at new moon, and it happens because the moon itself gets in the direct line of sight from a place on the Earth and the sun. Now, it's just one of these bizarre coincidences that the moon is 400 times smaller than the sun, but it's 400 times closer than the sun. And what that means is it's almost the same size as the sun when we look at it in the sky. And that means that the moon, if you're positioned just right, can completely cover the disk of the sun, and you would get a total solar eclipse. Now, that only happens on a very small area of the Earth. So you can see in this diagram here, the total solar eclipse would be happening in this little zone here where the moon is completely hiding in the sun and there's no sunlight falling. A partial eclipse will happen just out with that zone. And for those that are interested, there will be a partial eclipse of the sun on the 10th of June this year. And Caithness Astronomy Group will be trying to observe that. So if you check out our website near on the time, we'll provide more details, and hopefully we can do a bit of live streaming of the eclipse happening. If you do decide to watch the eclipse yourself, it's important to adhere to some eye safety precautions. We can explain more of that near on the time. So that's a solar eclipse. A lunar eclipse happens when the moon passes into the shadow cast by the Earth. And because the Earth is much larger, the whole of the moon can pass into that shadow. So you can have a total lunar eclipse, but you can also have a partial lunar eclipse as well. Now, the lunar eclipses can only happen at full moon, because clearly it can only happen when the moon is on the opposite side of the Earth from where the sun is. Now, you may be thinking to yourself, well, we have a full moon and a new moon with a 2-week break in between. Why don't we have eclipses every full moon and every new moon? And the answer to that is that the moon orbits the Earth at a slight incline compared to the orbital plane between the Earth and the sun. So eclipses are actually reasonably infrequent, and you probably only see a few per year from the Earth. And that's all due to this slight difference in the orbital planes between the moon going around the Earth and the Earth going around the sun. Right, a few other useful facts to know about the moon's orbit. The moon's orbit is elliptical. So that means it's oval in shape, it's not a perfect circle. And what that means is sometimes the moon is slightly closer to the Earth and sometimes it's slightly further away. And that means that the moon's apparent size in the sky will vary slightly. So on the right-hand side, the top corner here, you can see that the change in size is not particularly significant, but it is noticeable if the moon is particularly close. It does appear that little bit brighter than if it is at its furthest point. And you've probably heard in news headlines things like supermoon. Well, supermoon is when you have a full moon happening at the point of the closest part of the orbit. And the opposite is referred to as a micromoon, although you'll see between the two, there's not that big a difference in size. Okay, we've already mentioned about the tilt between the Earth and the moon versus the Earth Sun orbital plane. So I'll skip beyond that one and talk about tidal locking, or the technical term for it is synchronous rotation. And the animation on the right-hand side shows what I mean by that. You can see the Earth in the centre and the moon orbiting around. And tidal locking means that the moon rotates once on its axis over the length of time it takes to orbit the Earth once. And a consequence of that is the face of the moon, so you can see where the eyes of the moon are looking here, the face of the moon always, sorry, the same face of the moon always points towards the Earth. And that means we can only see essentially one half of the moon. We can't see what's often referred to as the far side of the moon, which is a topic that Keith Nicholson will be talking about tomorrow. Now, it just so happens we can see a little bit more than half because of the fact that the moon, the Earth-Moon orbital plane is slightly different to the Earth-Sun, and it's an elliptical orbit. We have an effect on the moon called libration, which essentially means that over time, it appears to wobble a little bit. So you can see in this animation here that the moon is growing and shrinking, and that's due to the elliptical orbit. You can see that it kind of nods up and down the way a little bit, and that's because the moon orbit around the Earth is tilted 5 degrees relative to the Earth's orbit around the Sun. And because it's an elliptical orbit, at certain parts of the orbit, the moon sort of speeds up a little bit compared to other parts, and that means you can see around the edges a tiny amount. And the outcome of that is that you can therefore see roughly 59% of the lunar surface if you observe it for a lengthy period of time over probably better part of a year. Now, recently, I was able to glimpse the far side of the moon, or one of the features that's on the far side of the moon. And the feature is a giant impact basin, Mare Orientale, which is about 1,000 kilometres in diameter. And that's big enough that the UK could easily fit in the middle of it. And it's only partly visible. It's only partly visible during favourable libration, when that part of the moon is tilted a little bit towards us. And in the photograph above, what we are seeing is this part of Mare Orientale on the very edge of the moon. So that crater there is this one up here, and that crater there is this one. And hopefully you can see the arc of the outer edge of the impact basin, and then there's another one there for the next part of the impact basin there. So why am I mentioning this? Well, it's a bit of a sneak preview to what Keith will be talking about tomorrow, and it's also to highlight that when I was talking about the massive impacts on the surface of the moon and showing you photographs yesterday, when you see what the far side of the moon is like, it is quite noticeably different. And one of the big reasons why it's different is all down to the thickness of the crust, and therefore the scars left behind by the impacts on that side of the moon. So you can see here from satellite data from a NASA mission known as the Grail mission, and what it did was it used gravity measurements to assess the thickness of the crust. It used two satellites in the Grail mission named Ebb and Flow, and those two satellites were able to map the thickness of the crust by various measurements. And you can see on the near side of the moon, which we've been looking at yesterday, and I'll show you some photographs of today, you can see there that there's a lot of this side has color coding in the blue and green zone, which is down the thinner end when you look at the crust thickness, whereas the far side of the moon, there's a lot of it is in the yellow and red end. There isn't here, but that's these blue bits are really big impacts that have happened on the far side. And there's Mare Orientale, there in that big blue zone that you can see. So just a few slides I'm going to show here that I'm showing simply because the telescope observing isn't able to be carried out tonight. So I'll give you an idea of the sort of things that you can see. This is the phase of the moon at the moment tonight, and you'll see it's a slightly larger proportion is visible compared to last night, for those that joined us last night. If you want to download the software that generates this, and there's a link there at the bottom. It's a virtual moon atlas, and it will allow you to see detailed views of the moon, and you can click on them and find out what you're looking at, and it gives lots of descriptive information on it. Now, there was a question last night on whether you were able to see the leftovers of the Apollo missions on the lunar surface. And here we have 6 photographs taken by the Lunar Reconnaissance Orbiter, which at certain points is orbiting the moon only about 30 kilometers above the surface. And it's been taking lots of detailed images across the surface of the moon for quite a few years now. And here are the images taken from the 6 Apollo landing sites. And if you look at the images, now obviously they have been annotated to make it clear, but you can see the leftovers of the landing spacecraft and little footprint trails across the surface of the moon as the astronauts have gone to and fro doing experiments, collecting rocks, etc. And in this bottom one here, you can even see the lunar rover parked off to the side. So in response to the question, yes, you can clearly see the evidence. You can't see that in any observations from the Earth or even from the Hubble Space Telescope, but the orbiting spacecraft are able to pick up these little details. And tonight, if it was clear, we could have pointed out 3 of the 6 Apollo landing sites. So there's Apollo 11, so that's the one that everybody certainly knows, landed in the Sea of Tranquility in 1969, and that's the location there. So it's quite easy to pick out the dark patch of the Sea of Tranquility with the naked eye, and it's on the southern part of it that the Apollo 11 mission landed. Then Apollo 14 was a bit further south of there, so it's in a more cratered region. Apollo 17, the last mission to land on the moon, it landed very close to the edge of the Sea of Serenity, which is the one that's above and to the left of the Sea of Tranquility. So you can see here on the right-hand half of the moon, there are 3 Apollo missions landed there, and it just so happens that there are the other 3 on the other part, although one of them is pretty close to halfway in the middle. Now, I'll just point out for reference for those that were watching last night, where a couple of other craters are that were highlighted. The crater Theophilus is here. You'll remember last night, the terminator, the boundary between nighttime and daytime on the moon, was stretching up roughly along this line, and it's now shifted quite a sizable amount over the space of 24 hours. So the moon appearance does change quite rapidly during certain parts of its orbit. And here we've got the Messier craters, which with a close-up kind of looks a bit like a dragonfly. So you can see the 2 craters there, the long body of the dragonfly and the ejecta also forming wings going across that way. And probably worthwhile pointing out that the crater here, Theophilus, is adjoining the one beside it, Cyrillus, and you can tell which crater was there first by which of the rims is more intact. So because the crater Theophilus has that circular form, and Cyrillus has what looks like a chunk bit out of it, that tells you that this impact crater formed after this one. So you can make sense out of the crater patterns as to the order in which events happened on the moon millions and billions of years ago. A couple of other photographs, really just to show you what you would have seen on the lunar surface had we been able to point the telescope at it tonight. So it's just a selection of detailed craters. That's the sort of view you'll get from a fairly small amateur telescope. You don't need anything really big and expensive. The moon is something that you can see in lots of detail with fairly basic equipment, such as the one in the top left-hand corner. So that's the one that Christian would have been using tonight. And on the right-hand side, you saw a video clip there. So that was live footage of the surface of the moon. And it was on a night when the atmosphere was quite turbulent. So it was quite windy. There was lots of heat rising after a hot day. And you can see the effects are it causes the highly magnified view of the moon to shimmer. Now, when we capture that sort of video footage with specialized astronomy software such as SharpCap, video capture software, we can capture high frame rate video clips and then process them to get very sharp still images. So let me just very briefly talk you through this just to wrap up this evening. You can see on the right hand side here we have the live image, and you take it into software such as Registax or other freely available software, and what you do, or what the software does, to be honest, you will have to click a handful of buttons and it does all the hard work for you. The software takes the best and sharpest frames from your captured video. It will get rid of the fuzzy ones that are blurred, they're out of focus. It will take the best ones and align all of them. That's what the red dots are doing. It's picking out features and it's then going to align all the separate frames. It will then stack all the frames, and that could be hundreds or even thousands of individual video frames. It will stack them into one still image, and you'll see that that stacked image is already sharper than some of the blurry ones. And then the software has special sharpening algorithms that can pick out, allow you to pick out the detail, and you can get a very, very clear, sharp, detailed image that way. So that's a bit of an overview of how we can take slightly shaky, blurry images of the moon and planets and get sharp, still images to counteract the effect of the Earth's turbulent atmosphere. So that's all I'm planning on covering tonight. The moon is such a fascinating subject. It's something that we could have a year's worth of talks on, because there's lots of interesting things and there's been lots of work done in it because it's our nearest neighbour. But I think that's probably enough for this evening, and hopefully it provided a bit of a taster for what you can do observing wise for the moon, and a bit of a preview as to what the next talk is tomorrow evening that Professor Keith Nicholson will be covering on the far side of the moon. Okay, so how are we doing questions wise tonight?
Yeah, one or two coming in. First question that's live is from Williamson's, asking, is the moon hollow or solid?
This sounds like a geology question, but it's probably one that I can handle, Keith. But feel free to pitch in with more details after I've covered the basics. When the moon formed, back when it had that really massive collision that led to the moon being generated 4.5 billion years ago. Initially, the middle of the moon was quite liquid, and the crust eventually cooled and hardened. But it would have taken a long time for the inner parts of the moon to then start to cool further. And I believe at this stage, unlike the Earth, which is a bit bigger and for a number of reasons still has molten rock in the middle, I believe the moon is pretty much solid. And I used the term yesterday, and I was kicking myself after it. I said it was the moon was geologically dormant. I think dormant's the wrong word, and Keith can maybe tell me the right one. I think it's basically geologically dead, that there's not much in the way of things happening because it's by and large solid. But Keith, if you want to pitch in and either correct or give extra details, feel free. But simply to answer the question, it's solid. I think is the bottom line in answer to the question that was asked.
Yeah, thanks, Gordon. Yeah, you're absolutely right. That was a good description there. And there's no geological activity or volcanic activity on the moon now. That's all past. We had a question last night about are there plate tectonics, or have there ever been on the moon? And there's no evidence for that. And I was trying to remember last night the only other body in the solar system that may have some plate tectonics is the moon of Jupiter, Europa, but that will be very different from the tectonics and the plates that we see on the Earth. More likely water ice type plate tectonics than the silica crust that we see today. But there's no activity on the moon now. In fact, the moon has been really dead or inactive from geological activity now for tens of millions of years. And as Gordon said, it doesn't possess the active core that we see on the Earth today.
So, and I noticed there's a kind of linked question just came up. It says, could the moon have a core of ice? And I think I'm quite safe in saying that the core is going to be metallic, just like the other rocky planets, including the Earth, where while it was in the kind of hot molten formation stage, what happens is that the denser constituents of the planet or rocky body have the denser bits have sunk to the middle. So you end up with what the Earth has, which is a metallic core, mostly iron, because that's the main metal that's there. So I think an answer to that is not ice, but it's metal. It's not to say that smaller bodies further out in the solar system may have a core of ice, but the rocky planets near the sun, I think I'm right in saying, Keith, they're all metallic cores, probably iron cores.
Yes, that's absolutely right, Gordon. And the only thing that differs really is the size of the core relative to the size of the planet. There's some variance on that, and the moon core is in proportion to the size of the moon is greater than the size of the core on Earth. And that's the only sort of variance we see. But in terms of composition, yes, you're absolutely right. It's all metal, nickel, iron, just the sort of composition we see in a lot of asteroids.
Okay. I'm seeing a question here from David Shand. Are there any coloured mineral patches on the moon's surface rather than shades of grey? I think it kind of looks like shades of grey when you're viewing it from the Earth. But if you look at the image that's the backdrop on my screen at the moment, you will notice that there are lots of darker patches there, especially on the right hand here. So you can see sort of dark zones there. They're not black. This particular image is a monochrome image. If it was taken with a colour camera and the colour kept as part of the image, and you oversaturate the image, colours will start to stand out, and you will see kind of reddy browns and that. I think that's probably going to be down to iron type minerals, but again, Keith being the resident geologist in the group, you might be able to elaborate on that. But there is different minerals on the surface, and it does give a degree of colouring, but by and large, the rocks don't look nice and brightly coloured that are on the surface.
Yeah, that's right, Gordon. I mean, a lot of the rocks on the moon are actually quite fine-grained, a bit like basalts that you see, and as such, they tend just to look quite uniform. And that's just by the way they reflect light. You know, if you look at a granite, it looks quite white or white and black, sometimes reddish black as well, because the crystals are quite large. The basalt crystals are really small, and so it always looks black and dark. But the one really interesting thing, and I was fortunate enough to actually be alive when all the Apollo missions were on the go, and watched them live. And one of the most exciting ones from that color point of view is Apollo 17, which is the only Apollo mission to have a geologist, a qualified geologist on board. And there they discovered orange soil. And I well remember the geologists getting really quite excited to it. And they've brought samples of that back. And I'm very lucky to have been able to examine moon rocks and in thin section. And that orange coloration was due to very fine globules, if you like, glass-type particles of ejecta that have been brought into the or built into the soil or the regolith. And that was very, very unusual, and we haven't had any other examples of that, simply because we just haven't had any more lunar exploration. But it's something that we want to explore even further with some of the remote missions that will bring back samples to Earth, because these are really quite fascinating variances in the geology that we want to explore further.
Okay. There's a question here from Eleanor. Is there plans to land on the moon again? Now, there was a recent mission launched by the Chinese, where they sent a spacecraft to the moon. It collected some samples and brought them back to Earth. I think that was last December that happened. And that kind of ties in with what Keith has been talking about, that it's much better to be able to bring the material back to the sophisticated labs on the Earth and do the detailed science on them there. So there are ongoing missions to the moon, whether to orbit it and gather data or to land on the surface and bring back information, either transmitting it or actually bringing samples back. But in addition to that, NASA has plans to send people back to the moon during this decade. I don't know the latest timescales, but if you do a search for Artemis, that's the name of the missions that are going to send people back to the surface of the moon. So I think there's a mythological link between Apollo and Artemis, but I'm afraid my knowledge of that area is not good enough for me to tell the story behind it. But if you Google Artemis missions to the moon, you'll get some information on that. Right, next question from Gary in Stonehaven. So, hello Gary. Given that it's almost 50 years since we landed on the moon, do we know all we need to know? Well, that's not a question to ask a scientist. Scientists never know everything that they want to know. We know lots, and we know lots more now than we did 50 years ago. So in answer to your question, it's no, we don't know all we need to know. If the question is, do we know all we need to know to get there and back safely? With the technology and our understanding having improved, we should be able to do it safer than we did years ago. But hopefully that answers your question rather than a simple no answer. Okay, is that all the questions? Are we?
That's all the ones that we have at present.
Okay, but that sounds like a good time for us to wrap up. So I'll thank Keith for pitching in with the technical bits as he did last night. It's when you're talking about rocky bodies, it's always good to have a geologist at hand. So thanks to Keith, and Keith will be doing the presentation tomorrow night. So excellent. Oh, I've just got a quick message here from Neil. You mentioned that Artemis was the sister of Apollo. So there you go. That's the link between the two. Thanks for that, Neil.
Thank you, Gordon. Thanks for presenting again this evening, and big thanks to all our audience too, and for Keith for helping with the geology questions. That's great. So we're looking forward to the final installment, part 3 at 7 p.m. tomorrow night, the 21st, from Professor Keith Nicholson, The Far Side of the Moon. So upcoming events we've got on Wednesday, the 24th of March at 7 p.m. Magnus Davidson from Environmental Research Institute in Thurso will join us to explore the offshore wind potential found around the coast of Caithness and discuss how new and existing developments can benefit us at a local, regional, national and international level. He will also look at the plans for the Pentland floating offshore wind farm off Dounreay and into the wider potential from the new ScotWind leasing round. Then on Thursday the 25th, again at 7 p.m, we'll be joined by former astronaut Digger Carey and his wife Cheryl for a reflective and entertaining look how they built a life and family together. After meeting in high school, they achieved liftoff in the military and then soared with NASA. But it wasn't always smooth sailing. Learn the highs and lows of serving your world with pride and keeping it together while raising a family. There'll be a question and answer session to follow. And just a plug, on Friday the 26th, Murden Murray will be presenting the science of gin, which the whole committee are looking forward to. I think everybody else. You can find these details online at science03.org, and the activity booklet is available online for download. So to all the panel, thanks for helping out tonight. Thanks for joining us, audience, and we'll say goodbye till tomorrow night. Bye-bye.